Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Hello and welcome back to the 18th edition series, and today we are covering part 3, Assessment of General Characteristics. So we've already covered now an introduction, part 1 and part 2. This is where we actually start thinking about doing an installation. So Assessment of General Characteristics starts with 301, 301.1, and it's basically saying that an assessment shall be made of the following characteristics of the installation in accordance with the chapter indicated. So we're going to look at the purpose for which the installation is intended to be used, its general structure and its supplies, external influences which it will be exposed to, compatibility of the equipment, maintainability, safety services, and the assessment for continuity of service. So let's start with purpose, supplies, and structure. So you're going to do a new install or a new design. You need to know what the client intends to do with the electrical installation. Why is the work being done? Is it due to growth? Is it due to increase in demand, change of use, change of occupier, change of ownership, an insurance rewire, refurb, redo? Number of reasons, but if we find out what the purpose is for the electrical installation, we can understand the intent and we can then help with our design. One of the things it says there, maximum demand or diversity, common question criteria, this one. So 311, for economic and reliable design of an installation within thermal limits and admissible voltage drop, the maximum demand shall be determined. In determining the maximum demand of an installation or part thereof, diversity may be taken into account. So, with regards to a distribution circuit and subdistribution within an electrical system for a large site, you will consider the equipment being connected and the use of it, the demand of the equipment, and then you decide with your distribution what sizes to make. This illustration here, this graph shows you a typical arrangement for a domestic customer by household size. So here we've got midnight, 4 a.m., 8 a.m. So we've got a one person household. Wakes up, bit of breakfast, goes off to work, nothing being used today, so this is just idling equipment, and then a bit of dinner and then bed. Move someone in for 2 persons, a little more effort of demand for breakfast, and then maybe the oven went on for dinner, not the microwave, so a bit more power demand, maybe there's a shower. And with 3 persons, you can see there's more. 4 persons, there's a big jump in the morning and a bigger jump for the shower. And 5 persons, which is my household kind of style, right at the top, lots of demand. So different uses of the system, different characters of demand. We have to consider the demand of equipment, and then we apply diversity to that. Now, there is good guidance in the on-site guide. I have done a video in the 2396 series on maximum demand if you want to do, but for now, with the regulations, all we really need to know is it's for economic and reliable design and thermal limits and admissible voltage drop. Okay, and then diversity taken into account. These are the key things we're looking for here. 312. This is conductor arrangement and system earthing, so it's just a introduction to tell us that we need to identify the number and type of live conductors. So we're going to do a new design or a new install, and they require 3-phase, but they only have single-phase. Problem. They require 3-phase, and they want to run a single-phase piece of equipment, so they'll need a star 3-phase because of the neutral for single-phase equipment, but they only have delta. Problem. So we need to understand the type of live conductors, the number of live conductors, and make sure the supplier, also the client, will be adequately provided by the supplier for that. There are illustrations given over the next page that highlight the arrangement of these live conductors. So do study those and do familiarise yourself with those. In your exam, you'll have an illustration of one, and it'll ask you which it is. That shouldn't be too tough. We then have earthing arrangements, types of system earthing. I've covered this in other material before. So when we look at system earthing, we need to understand what the letters represent. So T, N, S, T, N, C, S, T, T, etc. So T stands for Earth, or Terra, French for Earth. N is neutral. S is separate. C is combined. I is isolated. Those are given there. We need to understand how they're used. If you turn the page, you will have poor drawings, but drawings nonetheless, of the three common earthing systems. So we have the TNS, the TNCS with the PME, and the TT. Now if you look at the two TN systems, so figure 3.8 and 3.9, you can see with them that there's one source Earth, and then Earth comes in. So it's Terra, and then it's neutral. Now with the TNS, it goes to neutral, but then it's a separate protective conductor in Earth. So a separate Earth is run. And so you can see there's an L1, L2, L3 neutral and protective conductor line. If you look at the TNCS though, with the PME, it actually stays as a combined conductor. And so it's only a line 1, line 2, line 3, and a combined conductor known as a pen. And then the separation occurs in the client's end. So if you don't understand the difference between those two drawings, do study them a bit more. Over on the next page, the TT is a lot easier. There's a source Earth, and then there are installation of electrodes. So there's no combined neutral and Earth connection after the system. Right. Your exam, you may have a drawing like this. Just make sure you identify the earthing system. Some people still struggle. If you don't know your earthing systems off by heart, let me know and I'll try and provide some extra content for that. The next one is 313, supplies. And there are a number of questions that come in with the words characteristic and supply in it. So surprise, surprise, it's a supplies characteristic, and it's here, 313. So the following characteristics of the supply or supplies from whatever source and the normal range of those characteristics where appropriate shall be determined by calculation, measurement, inquiry, or inspection. So, the normal voltages and its characteristics including harmonic distortion, prospective short circuit current, nature of current and frequency, earth or loop impedance external, suitability for the requirement of the installation including the maximum demand, and the type and rating of overcurrent protected device. Now, you can have a question ask you which of these could be measured, which of these could be inquired. So do make sure you understand how each of these could be obtained. Some could be obtained by a number of ways. But these are all supply characteristics. And what this means, if I was going to do an installation and I've ascertained the number of type of live conductors, the earthing arrangement, the maximum demand, what the client wants it to do, I still need to know what the voltage is, what the frequency is, and I need to know what the ZE is and the prospective fault current is. Because if that prospective fault current is 8 kA, I can't select 6 kA switchgear at the consumer. I've got to obviously upgrade that to 10 kA or 20 kA. If the earth fault loop impedance external, let's say it's a TNS system, I can assume it to be no more than 0.8 ohms, but if I actually measure it and I get 0.55 ohms, I then have a value to work with for my values of ZS with my designs. And it's much better to have the actual values because then you can understand the actual ZS's, and that will help you understand the energy levels in fault currents. We'll cover that more in chapter 43. And then we have 314, division of installation. I see so many questions coming from this section. It's quite crazy. They like rewriting these ones. So, every installation shall be divided into circuits as necessary to avoid danger and minimise inconvenience in the event of a fault, facilitate safe inspection, testing and maintenance, take account hazards that may arise from the failure of a single circuit like a light circuit, reduce The possibility of unwanted tripping from RCDs due to excessive protective conductor currents, not due to a fault. Mitigate the effects of electromagnetic disturbance and prevent the indirect energizing of a circuit intended to be isolated. Now with these, I would say, quite often you get questions with these, but with these, right, so avoid dangers and minimize inconvenience in the event of a fault. So this could be where you have a fault occur and then you have a power loss which can create further danger. To facilitate safe inspection, imagine that you were in this installation and you had no way of isolating just this circuit. You would then be encouraged to work live because you wouldn't want to isolate this and turn off all of this. These are the kind of things that we're saying. You should ensure that you have switchgear, control gear and isolators as local to the point of isolation as possible to facilitate safe inspection, testing and maintenance. If you require a larger part of the installation to be isolated, then sometimes that can be considered as not reasonably practicable, or sometimes the work will be planned at a much less frequent interval, which again is not suitable for the life of the electrical installation. Take account hazards that might arise from the failure of a single circuit. In typical domestics, we'll have on this RCD upstairs lights and downstairs power, and then up here upstairs power and downstairs lights. So that should one go off, you have the other. You know, you get that. I may have said that wrong, but you get the arrangement. The idea is to always have a power supply on a level so you may be able to facilitate lighting. Unwanted tripping, we're going to cover that later on. With regards to that, there's new requirements in the 18th edition for unwanted tripping. Okay, and we'll cover the others as we go through. But do remember 314, highlight this one if you are highlighting, because a lot of questions come back here. Okay. Whenever I mention division of installation, I'm thinking of these. I am thinking of these when I mention division of installation, so do kind of repeat these in your mind as much as you can. Compatibility, chapter 33. Notice chapter 32 is not there because it's referring to a later part. So the compatibility characteristics. We've got an assessment is made of any characteristics of equipment likely to have harmful effects upon other equipment or other services, or likely to impair the supply, such as coordination with concerned parties as petrol stations, kiosks and shops within shops. Yeah, it's quite frequent. I was in a petrol station just the other day that had a subway in it, and the subway tripped the power out and they had no lighting in the service station. There wasn't effective division in that case, and there was poor compatibility. Now, things that can create compatibility issues. So we have transient overvoltages, undervoltage, unbalanced loads, rapidly fluctuating loads, starting currents, so your motor starting could flicker the lighting in the other person's area, that kind of thing. Excessive leakage currents, protective conductor currents, feedback, power factor, etc. So this illustration shows you an RCD and it shows you a filter to equipment, and then there's a fault. But what we've got here is we have protective conductor currents due to interconnected equipment. So this, we're going to explain protective conductor currents later, but this is current flowing in the protective conductor system that's not due to a fault. It's due to filtering, or it's due to suppression, and quite often, we have to watch these levels, and we're going to cover this in chapter 54 as well. But this shows you current not due to fault. This shows you current due to a fault, and then this is current due to filters. This is illustrating the three types of currents that can occur on the protective conductor. We need to make sure we have effective compatibility with that. We then have maintainability, 34. Assessment will be made of the frequency and quality of maintenance the installation can reasonably be expected to receive during its intended life. The person or body responsible for the operation or maintenance of the installation shall be consulted. Those characteristics shall be taken into account in applying the requirements of parts 4 to 7, so that, having regard to the frequency and quality of maintenance expected, Any periodic inspection and testing, maintenance and repairs likely necessary during the intended life can be easily, readily and safely carried out. The effectiveness of the protective measures used, which we'll cover in chapter 41 in the next video, will not diminish. So when we go to maintain, the protective measure for basic protection and fault protection will not be diminished. Quite often when we open an enclosure, we may be removing a barrier, maybe removing basic protection or additional protection. We need to make sure that we don't diminish the life or shorten the life or reduce the efficiency of that. And then we have the reliability of equipment for proper functioning of the installations appropriate to the intended life. So we've got to make sure that we understand the intended life and the equipment functions for that purpose. Then we have safety services. Safety services has its own section in part 5 later on, but this just briefly mentions that the following electrical sources for safety services are recognised. We have storage batteries, primary cells, generator sets, and separate feeders. So these must be considered at this stage, and there's a whole separate section for them in part 5. And lastly, 36, continuity of service. Now obviously, depending on the environment, I mean, this might be a medical location, this might be a data center, so there could be two issues here. Medical location, continuity of service, it's obvious. If you lose power, IT equipment maybe needs to have an installation monitoring device to raise an alarm. If you have a data center, you may have a residual current monitor or an installation monitoring device to, again, raise an alarm. What you want is a single fault condition to stay in service but have an alarm system in place. This introduces the IT system, which we'll talk about later on. So we have to think about the selection of the system earthing. The IT system might be a good idea. Select the protective device in order to achieve selectivity. So again, we want RCDs, then we need to achieve selectivity. Time delay RCDs, for example. Number of circuits. Divide the installation up into more circuits so that if there is an isolation, the other parts are not disconnected. In medical locations, socket outlets in medical IT locations or medical operating theatre locations are often supplied by two separate circuits, so that if one was to fail, the other one is still there. Multiple power supplies, that's what that is, and the use of a monitoring device. So there are a number of ways to achieve continuity of service, and we'll cover them later on in part 5, and we'll also probably preview them in section 7.10. Okay, so these are the assessment of general characteristics, all the little things we need to consider and the decisions that we need to make with regards to it's like a survey of the installation, so let's go back to the beginning. So what is the system for? What's it going to be used for? What's the demand placed upon the system with regards to diversity, thermal limits, voltage drop? Okay, what existing live conductors are there? Have I got single phase or three phase? Do I have a neutral? What's my system earth? Do I have a TNCS or a TNS, or am I stuck with a TT system? I need to know this. This all affects my design later on. What is the supply characteristics? What's my existing ZE? Is it any good? Is my prospective fault current okay for the switchgear I've decided to use? What is the current and frequency? Do I have enough power supply? When I do that, I need to divide. Do I need to divide the system up further? Is there an existing system that I need to divide upon? And then we have compatibility. So I need to make sure that anything that I install does not impose or affect the equipment adjacent to it. There's number of ways that this can occur. I need to consider maintainability in the future, so I need to make sure that if I have connections up high in an inaccessible position, that I put connections that don't need maintenance. If I do put them up high and they do need to be maintained, that there is provision for ease of access, such as a platform or a hatch or something. Make sure the connections are in accessible positions, readily accessible and easy to identify. I then need to make sure that I've considered any safety services and the sources of supply for those safety services. Could be something as simple as emergency lighting in a pub, or it could be a larger sprinkler system or a larger fire alarm system such as a communal care home. I've got to make sure I've considered the need for those selections, and later on in part 5 I will select for those. And then lastly, is there also a further need to make sure that if there is a loss of supply, there's still a power supply, such as a medical location or even a data center where a loss of supply could be financially disastrous. So, I've got to consider all these things at this point. Once I've made these assessment decisions, I can then go on to select the requirements for protection against electric shock, protection against thermal effects, protection against overcurrent, protection against overvoltage. And that's what we're going to start approaching in part 4 next, with chapter 41. See you then.